Hi, good morning, everybody, and welcome to the Informatics Power Talk seminar for Friday. And I'm very, very privileged to introduce today's speaker. It's our own Dr. Jim Cimino, and he's chair and distinguished professor of the Department of Biomedical Informatics and Data Science in the Heersink School of Medicine at UAB. I don't want to take too much time introducing him, but long distinguished career, has many honors and awards and involvement. His current research involves developing systems for clinical and translational researchers and exploring new ways to improve the EHR, which is one of the topics he's going to talk about today. So, Dr. Cimino.
Okay, thank you, Amy. Some of you may remember some of the slides from a previous talk. Some of you probably weren't born yet when I gave the previous talk. Actually, it was 2018, if anybody remembers 2018. So I'm going to build on sort of where we've come, and of course, a lot of things have happened in the interim. There we go. Okay, so I'll talk about how we used to develop electronic health records, about evolution or creation of new electronic health records, and really the reinvention of the electronic health record, which is kind of my exotic goal. We'll talk about what's going on in clinical informatics, especially given the rise of generative AI, large language models, and whether that has really killed clinical informatics research. And I'll talk about strategies and opportunities going forward. Okay, so if you don't know this diagram, it seems pretty obvious. The person plus the computer is writing the computer. Chuck Friedman wrote about this in 2009, called it a fundamental theorem of biomedical informatics, but of course it could apply to anything. And we'll come back to that later. So in the good old days, we informaticians would sit around and go, oh, we have a computer, let's build something cool. And we would build it and deploy it and see what happened. And there were no IRBs, there was no safety committee, there was just a bunch of guys in blue jeans building stuff and giving it to the guys in white coats and seeing what would happen. And electronic health records came out of that. We built some that were commercial ones around for decades, but they weren't really catching on. They were expensive, they were clunky. So we built ones in our own institutions, places like Columbia, Utah, Stanford, not Stanford, Harvard, Vanderbilt, and so on. And here. Okay, so and then if you remember when the World Wide Web was new, certainly some of you weren't born then, but anybody with Notepad or whatever the equivalent is on a Mac, it could build a website. You could just and so we did that at Columbia in 1 week. We were at a meeting. Somebody said, "Oh, this thing isn't right. We got to format it a completely different way." And I said, "Well, I saw this thing called HTML. It looks really easy to format stuff for graphical user interface. Why don't we build some tables of our patient data and then we can play around with the format?" And a week later, we had a working EHR and we showed it to the surgeons. They said, "Yeah, that's what we want." And we said, "Well, you have to buy some Macintoshes for the nursing stations to run a browser." And they said, "Well, we're surgeons, we have a lot of money." So they went out, a week later, they had these Macintoshes. And so 2 weeks from the time that I said, "Hey, I think there's this thing called HTML," to having a working EHR. Now that was because we had built an electronic health record already that was mainframe based, server based. And so we had all the infrastructure we needed. All we had to do was connect it up to a web browser. And so there was a paper in 1995 describing that, and this is a screenshot of one of the figures, and it's just HTML. So if you can't read it, the important thing is it's just text, and you can just write it with any kind of word processor you want, and then that would produce something that was graphical. And I apologize, I can't seem to find the original color image even online for this paper, but the point was that very quickly you could create something that was a new way to look at the data. Okay, so we've been trying to improve documentation for decades. First on paper, working with medical students, write better notes, and of course they write these big notes and then they learn to write them smaller as residents, and then as attendings even smaller. But it was always a question of trade-off of how much time they would spend, how neat their handwriting was, because they were writing quickly, and the content of the note. And so we found that if you can figure out what the carrot is, then you don't need to use the stick so much in the carrot and stick model. So WebSys, which was the system that we built at Columbia, had this controlled medication list that nobody would use it. And so You know, that's just a graph showing the number of people using it, and it was a small number of people. So one day I went into the room where the residents are writing their notes, and I took some papers out of the printer, started signing them. I said, "Oh, what's that?" I said, "Oh, those are prescriptions." And this was, you know, before there was electronic prescribing. And they said, "Oh, how'd you do that?" I said, "Well, you know that thing you won't use, that medication list, you won't use it because it's clunky and it's extra work and nobody really wants to do the effort." I said, "Well, I use it, and now there's a print prescription button." And so so that's the usage of the print prescription button. I went back and asked them, and that was November 30 or September 30th, 2002. And then those are weekly, that's weekly usage statistics. And then there's also unique users. I only told 4 people about this, and we didn't tell anybody else. They told people. We didn't advertise it. We didn't have a way to advertise it. We tried users, but it took off. Everybody was using it because they couldn't find prescription pads in the emergency room, so they would use this. And we finally could see what the people were prescribing because it was all all electronic. And it was because it reduced their workload. How did it seemed like it increased their workload? But what it did was people said, "Oh, if I put this in here, the next time the patient comes back and says, 'You remember those 20 prescriptions you wrote me last week? I lost them. Could you write them again?'" I mean, that would have maybe not 20, but 10 certainly. Now they could just chuckle, click a button, and print it out, sign it, and give it to the patient. Whereas before, you had to stop what you were doing and participants ask you to start an AI companion. Should I? Sure, why not? That's gonna do, but we'll find out. Okay, so the carrot on the stick. Stop making requests out there. All right, so one of the keys to this was ontology, which I'll come back from time to time. It was a key part of this. We built a terminology that was all the control terminologies of the different systems providing data to our clinical enterprise, put them all in one place and merged them together and added knowledge about the meanings of these things. Some of this knowledge was simply going, these are synonyms. Some of the knowledge was these belong in the same class. Some of the knowledge was actually semantic information about the meanings of the terms that linked them to each other, so that drugs were related to tests that measured the drugs, and drugs were related to chemicals that were in the drugs, and chemicals were related to diseases that were caused by those chemicals, and so on. Okay, and that was January, volume 1, issue 1, January 1994 of Jamie. So the first issue of Jamie. All right, so how did we get to these electronic health records? Well, we started with paper records. If you haven't seen those are paper records, and the colors are the medical record numbers, and so they were filed by medical record number, and that's how you found them. And they, you know, it seemed like a good idea, but of course people would hold those records, and so somebody would come into another clinic and you wouldn't be able to find the records, so you have to start a new folder. Or the folder would be, you know, the patient just got discharged from a complicated thing and now shows up in the emergency room. I need the folder. Where is it? It's in billing. It's night or the weekend, so it's locked up in the billing office and you can't find it, so you don't know what's going on. Or things were illegible because they're handwritten, or things would fall out and get lost, or they get wet. We had them at a warehouse, and the warehouse had a flood, and we lost decades of records on people. And eventually they said, you know what, we're not going to keep these old records anymore. We can't find them when we need them, so we threw away Eleanor Roosevelt's tuberculosis records. And so so there were problems. But when we built the electronic health record, they said, what should it look like? They said, well, this is what the paper one looks like. Let's build an electronic version. And we got the early electronic health records. Okay, so when we were inventing cars back in the turn of the last century, we started with a horse-drawn carriage, and we went to the horseless carriage. And so, where do we want to go next? Well, we want to go to something like that, right? But that's not what happened. What happened was that we got a fancier horse-drawn carriage, because they just kept saying, well, what's wrong with this? Well, it's not enclosed, so we'll enclose it. And it's too slow, so we'll put a bigger engine in it. Or the engine blows up, so we'll put the engine, in the back or whatever. So they modified slowly, but they didn't stop and go, look, we don't have this horse thing anymore. Why don't we think about what the car should really look like? It took us a long time to get to that. Okay, so what did we do instead? We started adding applications. So we said, okay, let's add drug ordering to the system. Okay, so that my prescription writer turned into a drug order, because at first we could send faxes, electronic faxes. So we could also do alerts and say, hey, there's something wrong with this drug order. patient has an allergy. It turned out though, that for every 100 alerts, we would get 80 of them would be false positives, things we didn't care about. And 20 of them were life-saving. That's supposed to be Superman down there. 20 of them were life-saving. So we had to go and ignore all those false positives, and in the process get overwhelmed by alerts and start ignoring the important ones too, life-saving. So that was a problem. So then we added progress. So that's a barnacle, if you don't know what a barnacle looks like. And then we added medication reconciliation, and we added adverse event reporting and discharge orders and all kinds of other barnacles to the system until you couldn't even see the original system anymore. And people started to feel like that. It's a statue off the coast of England. That's low tide. Okay, so people say, well, part of the problem is we don't have a good user interface. So what if we could build a perfect user interface? We just talk to the computer, it talks back to you, you don't have to write anything, it just records everything. What might that look like?
Alexa, this is Joan that's had palpitations for a month and now has an irregular heartbeat. Has she ever had an arrhythmia before?
She doesn't have arrhythmia on her problem this day. This word appears 22 times in her health record and 350 times in reports from the Health Information Exchange. Would you like me to read them?
Yes.
Okay. Admission note from 1995 states patient has no family history of arrhythmias. Admission note from 1996 states patient has no family.
So there's no
history of
content,
arrhythmias.
right? It's just
Admission note from
information overload.
1997 states
Alexa,
patient has no
stop.
family.
Please order an electrocardiogram
So that's
Okay.
good, nice and
In
easy.
order for an electrocardiogram is in place.
and thyroid function test.
I'm sorry, Dave, I'm afraid I can't do that. Mrs. Jones had this.
So this is an alert.
Than 6 months ago.
But it's a false positive. The patient has a new problem. So it's okay to do the test.
It's in place.
Alexa, please schedule Mrs. Jones for electrocardiogram.
Now the system should give an alert here.
Let's
But it
take
doesn't.
the emergent scheduling.
And so the patient gets an electrocardiogram, throws a pulmonary embolism, she wasn't anticoagulated properly and dies. So the system, if it knew the patient had had this arrhythmia for a month, it would have said, oh, you need anticoagulation. And in fact, he said she had the symptoms for the month, but the computer couldn't make that connection. Okay, so if we started on another planet to build electronic health records, where we were unencumbered with these model patient records, what would it look like? If we said, let's build a system that will, more things for the program. If we could build a system to take care of sick people and make them better and keep them that way. All right, so my hypothesis was that we need to represent the why of patient care. Why do we think the patient has a symptom? Why am I ordering this test? Why am I choosing this drug? Why am I stopping this drug? All of these are important things to record in the record, both for continuity of care, but also for other things like for alerts, for research, use of the data, and so on. So the idea is to create formal representations of all of these facts that we put in the record: symptoms, exam finding, interpretations, differential diagnosis, and whatever else we start putting in there. We want to build the connections between these things. And then we name those representations as relationships. We say, this patient is on this drug to treat this disease, or this patient disease is being caused by this drug. So you don't just go, oh, look, everybody on this drug is on this, everybody with this disease is on this drug. You go, oh, they must be the treatment. No, it's causing the disease. You want to know the difference. And when it's stopped, you want to know the reason why it was stopped. If you're going to do outcomes analysis, it's important. Did the drug work? Did it not work? Was it too expensive? Did they forget to order it? Did they have a side effect? Those are all different things we want to model. And we want to model preferences and priorities, both for the clinician, preferences in sort of, this is how I want to treat this condition, and also the patient. Which things do I care about? Which things don't I care about? What's my priority? Do I want to keep my costs down? Do I want to lengthen my life? Do I want to reduce my symptoms? Those are, do I have religious beliefs that would restrict treatment that I get? All those. Okay, so I started working with folks here, Tiago and others. And we started working on, okay, what's the terminology, what's the ontology for representing this why stuff? And we call it different things. We call it decision making, but it's not about making decisions. It's kind of the decisions. So we call it the clinical care context. Created an ontology for that. And Tiago really took the lead on this, looking first at the literature to see what we could find, but then adding that based on reviews of records that we had in our own knowledge of understanding, and started and built an ontology that represented these concepts as classes. And it wasn't huge, All right, so now the idea is, what if we tell the electronic health record why we're doing something? So this patient has this symptom, and I want to know now, I'm thinking about arrhythmia. I think this symptom of palpitations is related to arrhythmia, and I'm ordering a test for that thing. And I say how long she's had that symptom. Remember, same thing as before.
Alexa, Mrs. Jones has had palpitations for a month and now has an irregular heartbeat. Has she ever had an arrhythmia before?
No arrhythmia is listed in any of the problems from the past 25 years of her health record.
So it's now looking,
And
it knows the
reports when
context,
health information is changed.
so it's able to prevent. the
Alexa,
information.
please order an electrocardiogram and thyroid function test.
Okay. Order-
Didn't have a problem ordering a thyroid function test because there's a new symptom,
Test has been placed.
so no false
Alexa,
positive.
please schedule Mrs. Jones for electrocardiogram.
I'm sorry, Dave, I'm afraid I can't do that. You associated her 1-month history of palpitations with her current arrhythmia, suggesting her arrhythmia has been present for longer than 1 month. Hospital policy is 1 month of anticoagulation prior to cardioversion. Would you like me to order these?
Yes.
Okay, an order has been placed for cardioversion for 1 month from now. Give him that Mrs. Jones is known to have C, E, S, 1 variant RS 2244613. Usual anticoagulation with diabetic abdomen is often indicated. Second line therapy is warfarin sodium. Since you were treating her for prophylaxis of related thromboembolic disease, the recommended target is between 2.0 and 3.0. Would you like me to initiate the standard therapeutic plan with warfarin sodium based on her weight, gender, and genetic markers?
Yes.
Okay. Orders have been placed for warfarin sodium follow-up throat time test, ended appointment and anticoagulation clinic.
Alexa, thank you.
You're welcome, Dave. Many people who have tried cardioversion have also chosen product from Amazon.
Okay, so what happened there? So the computer was able to do a lot more with that little bit of knowledge, just connecting the arrhythmia to a time, a 1 month history, right? It was able to connect the dots and could do a lot of things with that. Now, a couple of things about this. One is that recording, that was a fake. If you talk to an Alexa, you just say, Alexa, echo, and then say something, and then it'll say it. And so I just made a recording of that whole conversation. I told it what to say, it said it, and then I just cut out the part where I'd say, Alexa, echo this, and it cut out my parts and created that. So it was all fake conversation in 2018. But you could imagine having that conversation today. Back then I'm going, well, I don't know how we'll do this, but we'll figure it out. Well, today, very plausible to have that conversation with the computer and not have to do anything except pay $22 a month for ChatGPT or something, and you can do that. So we've got that part done. And the reasoning part's, maybe in there too. That's the thing we need to start to explore. The other thing I noticed is that I mentioned I put the word gender in my slide, so I should go take that out. So I don't, get in trouble with the NIH. Okay, so what happened? HITECH Act came along, Health Information Technology for economic and clinical health. And in there were incentives for physicians and hospitals, healthcare providers to implement electronic health records, $40,000 to every organization per physician. So a place with 1,000 physicians, that's $40 million. You can put in a lot of electronic health records, $40 million. And so what happened? Well, we got electronic health records, but there were some unintended consequences. One was the homegrown systems and small companies that were building innovative things based on those homegrown systems went out of business. The commercial EHRs that were in place at the time, back, blanking on the year, they were all in place, Epic, Cerner, Allscripts, they were all in place. And so they didn't have to innovate, they could just sell a product. So they've been trying to innovate since then, but they haven't had the same incentive because they haven't had as much competition. All right, so now we have vendors and IT departments, and they're telling us, the informaticians, sorry, you can't innovate. We don't want you touching these commercial systems anymore, we're just letting them run. So even the innovation at places like Columbia, Harvard, Vanderbilt suffered because of this new arrangement. All right. So meanwhile, clinical informatics. So this is the Woods Hole Oceanographic Institute and Marine Biological Laboratory at Woods Hole. And I taught a course, I led a course there for about 15 years, sponsored by the National Library of Medicine. And it was a 1-week course in informatics. We taught the whole spectrum of informatics. But I started off the week by telling people a case, a short case, of somebody who got paralytic shellfish poisoning by eating in a local restaurant. And then said, okay, now here are all the things we might want to do with this case where informatics could help us, and listed a bunch of questions. And then through the week, we'll say, okay, so see this question, how do we answer, how does informatics attack this question? And, went through it, natural language processing, decision support, bibliographic databases, all those things, that's how we kind of structured the course around that. So here's the case, and we'll make these slides available for folks so you can read it, but it's 50-year-old Native American female veteran who presents the emergency room, chief complaint of lip numbness, nausea, pain, and then has a history of present illness, physical exam, the progress, the labs, and radiology, EKG, and then a little bit of hospital course. It crams a lot of stuff into it. It's not a real case, but it could be a real case. And so then here's all these questions, and we won't go through all of these, but I gave a lecture on this just a year or so ago. And I said, oh, I wonder how ChatGPT would do with these questions. So I gave it the case, and then I said, all right, now let's give these questions. And I gave him each question. And I'll just show you what I did with a couple of them. So, well, let's talk about large language models. So generative AI, large language model, that's my acronym. That's my logo for it. And so, the definitions, you guys are familiar with this. Generative AI, artificial intelligence capable of generating text, images, video, other data using generative models in response to prompts. Learns patterns and structures from input training and generates new data that has similar characteristics. This is from Wikipedia, also from Wikipedia. Large language models, we use these sometimes interchangeably or together. These are the computational models for their ability to achieve general purpose language search and other natural language processing tasks. So the generative AI is thinking stuff up, and the large language model is saying it. One way to think about it. Okay, so what can we do with this? There's lots of stuff we can do. We can have it take the case and generate hypotheses. It can propose research. And it can do data and actually do data analysis, including writing program code, interpret research results, help you write manuscripts, or maybe write the manuscripts, clinical data interpretation, explanation. And so I do a year of review, and maybe you caught when I did this back in December, I gave this sort of a summary of this talk, but I do a talk at Amy every year in review. And in that, generative AI was the kind of a central concept that linked to lots of other concepts that were in the annual literature review of biomedical informatics. So, not a surprise. Okay, so if we look at these questions again, I'll just take a couple of examples. How do we keep clinicians from getting overwhelmed? So there was a lot of stuff in that case, and if it had been a real case, there would have been way more stuff. ICU data, lots more outside records, maybe health information exchange data, all kinds of stuff. And then the other one is, could this paralytic shellfish poisoning have caused the patient's myocardial infarction? As an internist, I knew about myocardial infarction, I knew about paralytic shellfish poisoning, but if somebody asked me this question, I would go, well, I've never heard about that. And when I learned about these two diseases, I certainly didn't learn that they had a connection, but let me think about that as an internist. What could they be? And I came up with some plausible explanations for why that would happen. Okay, so what happens with ChatGPT? I said, please summarize the patient's record, and it took that whole thing and turned it into this very nice single paragraph summarize. So that's something you can do. And if you said, now summarize it for somebody with an 8th grade education, we'll do that. Say for the patient, for instance. Okay. And so then I asked it about the myocardial infarction, and it first says, okay, so it's primarily a neurologic disease, but there may be some evidence that it caused a heart attack. Now, it didn't give me the evidence, but it can respiratory distress, can lower your oxygen, lower oxygen can affect your heart, and so it put that together and said, yeah, you can have myocardial ischemia just from hypoxia because you can't breathe, because you have a neurologic condition. So it put that together, which is exactly what I thought as well. Now, and then I thought, well, what if you have underlying cardiovascular disease? Then you're going to be even more susceptible to that. And so it came up with that as well. But in the end, it said, it's indirect, but it can happen. And so, which is exactly what I said in the class. So, well, maybe they don't need me anymore. Maybe we don't need clinical practitioners anymore. Okay, so we've got, generative AI, large language models. Maybe, we'll get rid of the informaticians and just let them do it. So, talk about learning health systems. We talk about taking data from the record and figuring out now how to improve patient care, and then get that knowledge that we create not just for writing grants, not just for writing papers, not just for getting Nobel Peace Prizes, but for putting it back into practice in the patient system. So if you haven't seen this, this is from the National Academy of Medicine, and this is their model of the learning health system. You get data, you use that as evidence for knowledge, and you put it into practice, that generates more data, and it's this virtuous cycle. Okay, so we want to reuse data for research, so we've got to get the data out. Then we want to maybe collect new data and get that into the EHR. So maybe we want to have the patient's Fitbit data, or we want the patient to fill out a survey that somebody's created in a research project. Whatever that is, we want to get those data into the EHR so they can be part of the patient's record for care, but then we can get it out for research. And then as we generate new knowledge, we want to introduce that back into the workflow. Okay, so that's great. That's what people talk about. The elephant is, people don't talk about, look at all those yellow boxes. Those are all projects. Somebody's got to do that. It says health IT in there. So you've got to go find a programmer and put that person on the project for 6 months and use up that resource to build one connection. And so the idea is for informatics has been, how do we step back from that, look at the general solution, so every time we have a new data, the kind of data we want to put in, or every time we have a new kind of data we want to get out, we don't have to build a separate box. We just, we just have a system for doing it. And that's exactly what we did at Columbia. That's exactly what I did at NIH. And I did it because I had an ontology. And so I didn't have to write a new program. I just put a thing in the ontology so that the program, the interface engine would say, oh, I know what this is. I know what table it goes in because you told me in this, in this other table. And when I get it out, I know where it is because I've got this ontology that tells me how to get the data out. And so we put a lot of work in there, but then every time you had a new data type, and we had 15 different systems plus 2 electronic health record systems that all put data into the record at NIH. We just added to the ontology and the interface engine took care of the rest. And HL7 standards, they all those things made it easy to do. The real trick then remains, how do you put that knowledge back into the system? And that's a tricky one because now you've got, knowledge could be anything. It could be do this, don't do this, do this, but only under certain conditions. And you've got to figure out how do you handle that in a general way. And how do you not only handle it, but how do you introduce it in a way that doesn't overwhelm the clinician? So you can say, oh, every time you have a new knowledge, write an alert. Put the alert in, well, remember that 100 alerts? Yeah, it'll be 1,000, it'll be 1,000,000 when we start putting people's genomes in there. So we've got to have a different way to look at that. Okay, so coordinated data collection, central repository for data reuse, and then some kind of institutional strategy. Not just, oh, we did a project, now we're going to put this in there. How are you going to do it? Oh, we're going to have a seminar and teach people. Oh, we're going to have a printed guideline that they have to read. Or we're going to publish a paper and then people will learn that from the paper. Or do continuing medical education, continuing nursing education. Yeah, that works for one thing, but it doesn't work for 100 things. Okay. All right. So one approach I took was thinking again about a table-driven, ontology-driven thing, was to take a look at the actionable genes from the American College of Genetic Medicine and create a table of those genes and of all the variants that are associated with them. And they provide a very nice website for all those variants and what diseases they increase risk for. And then and it was 24,000 rows right at the time that I looked at this. I'm sure it's more now. And then just create a table that can take the patient data and match it to those things, and then generate a list for the patient of things that the patient might have. And so the idea then is I can create a single set of recommendations for the patient based on their whole genome, based on that whole set of 24,000 variants. And part of the beauty of that is when there's a new gene, a new variant, I don't have to write a new program, I put a new row in the table. Okay, now, what about the actions? If every gene requires a different action, well, then maybe I do have to write a different program because I'm going to have all these things. So I went through those, not all 24,000, but I went through the 59 genes of 60-something diseases, and I said, well, what would the recommendations be? So that's 60-something recommendations. But what are they sort of generically? What do they look like? And so I created an ontology of those actions, of those recommendations. So things to avoid. Like don't jump on a trampoline or don't take this drug. It was all pretty simple. Don't jump on a trampoline is real because you could dislodge your retina in certain conditions. for your aortic valve or aortic root. Tell your relatives to get evaluated. Do things differently for pregnancy, monitor pregnancy earlier, but a lot of things around pregnancy management. Prevent the primary manifestations of this possible disease, or prevent the secondary complications by giving patients medication. You can't fix the disease, like, coronary artery disease, but you can lower the cholesterol, that kind of thing, to prevent the secondary complications. Follow the patient, do testing earlier than you would, do colon cancer screening, breast cancer screening earlier than you would normally. And then treat manifestations of the disease earlier than you would have, or treat them differently because this is a genetic condition, as opposed to just, run of the mill problem. And so it was only seven things. So I could build then, a report for that. So what did that look like? I could create a recommendation for Mrs. Jones. Well, she could have this reaction to general anesthesia. She should avoid trampolines. She should have her relatives evaluated for colon cancer. So you can see that, and maybe they get flushed out. Not everybody would have something that big, but maybe, somebody would have a few of those. And I can put it in one nice bite-sized thing, and then as new conditions are added, they're just added to that report. And the physician doesn't get a 27-page genomic informed risk assessment, which is what we do in the eMERGE. You get a nice little thing that looks like that. Okay, so now what? Now what do we do? Well, maybe we bring informatics back into the picture again. Okay, so more work on how we apply, let me see how I'm doing time here. Oh, great. How we make use of this semantic information that we want to get out of the record. Okay, so the idea is to actually create take the tables of data, the OMOP tables out of the patient's record. So all these facts, lab tests, vital signs, medications, diagnoses, procedures, events, visits, all that stuff. They go into OMOP tables, all these little facts. They're not related to each other, but we can relate them to each other using the ontology. So we create tuples that relate them to provide that clinical context. And so that, pretty straightforward. It's, again, you can do it with Notepad if you wanted to. And in fact, and then the idea would be we use that knowledge in some way to improve decision support, and that would be the experiment. It's like, okay, we've got this patient-specific knowledge base that we've created, the semantic net that relates all those facts from the record. Now what? What do we do with that? We're experimenting with that now. Okay, so this was from the original paper. When was that paper? It was last year's annual symposium. Okay, so
yeah, it was 2023. They published later.
Right, that's right. But the work was done. Yeah, that's right. It was 2023 annual symposium. Yeah. So this was a mock-up of what we thought it would look like. That we could have a timeline with those problems, and we could put various labs on the timeline. We could put medications on the timeline. We could relate them to each other. You can't see there, but there are little numbers here. So coronary bypass is a 2, and then that's related to this 2. And there's, allopurinol has a 3, and that's related to gout, and so on. So we'd have a way, some kind of graphical way to help people see those connections without showing them that god awful, semantic network. We wouldn't want to show them that. That would just scare them off. But so this was one version of that. And then again, continuing to look at how do we provide some kind of integrated display. And Tiago again did some work on surveying physicians to see what they thought about various ways of looking at data. This is the version that we have now and currently in development. There's all you have to see is that there's a timeline, and you can expand or shift the timeline however you want. There's problems on the timeline. Each horizontal bar or band is a problem, and then the things that are related to it are in that band there. So the medications, if there's an event, if there's a note, you can hover over the note and see a summary of that note, and so on. And now Tiago's doing a study now to see if we can use ChatGPT to generate summaries that will be acceptable to the clinician. Okay, this is just to zoom in. Again, as I said, we'll share the slides. You can take a look at these. But you can see sort of the semantics that we put in there. We may find a different way to represent this, but that's what we've got so far. All right, so this is the Wizard of Oz. That's the man behind the curtain. So we're creating this knowledge base. Originally, we started by, well, how are we going to create this knowledge base? Because people don't put this information in the record. They don't say why They don't put the Y in the electronic, they don't document it, or they might say it, but it's in text, so maybe we can use NLP to get it out. Maybe we can infer it because we know we have a knowledge base of drugs and diseases and say, oh, this drug is used to treat this disease, this patient has this disease, they have this drug, that probably related, so we can build up knowledge that way. We could take the whole database of, a million patients and go, show me all the people that have this drug and what problems they have, and we could figure out, use machine learning to figure out the relationships that might then apply to a specific person for a patient-specific knowledge base. And then, worst case scenario, we just get an internist to sit down and build the thing behind the curtain, and that's the Wizard of Oz approach. So this is the tool that we're creating right now. It's a very nice tool. Nick Timkovich is building. It shows you, for instance, notes. We use John Osborne's NLP to highlight stuff, and we can then pick out things and create linkages between different elements of the record, use the ontology to specify and so on. So it's clunky, it's not intended for physicians, it's intended for me to to build this, or any other physicians we might engage in this project at some point. But this is really just, this is to get it working. This is to be able to build a knowledge base to show people this is actually going to work. And then then we'll get all you guys to students to build different tools to do this. And of course we're starting using generative AI and say, hey, what are these? So here's the ontology. Here's a patient's record. Show me the relationships using this thing, and it's pretty interesting what it produces. Okay, so here's another diagram from way back. This is 1984. Marston Scott Boyce, written by Scott, wrote a book called Information Medicine, short little book, and in it he had this diagram, and he didn't really have a figure, he didn't have a caption for the diagram, he kind of explained it a little bit. And I talked to him and I said, hey, tell me about this diagram. And so the basic idea is that if you have some problem space, and over here on the right is sort of where you start when you see a patient. The patient comes in and goes, oh, well, I have my knees are hurting and I have a fever and I have this rash. And so there's like, what could this be? Is it infectious? Is it cancer? Is it rheumatologic? And so you've got this broad problem space, and then eventually you start doing tests, you narrow down, go, oh, this is clearly an infectious disease. What are the infectious diseases that give you rash, joint pain, fever, and you start to narrow it down. And what Scott Boyce said was that humans were really good using their pattern matching abilities to narrow down the problem space. So they look at this and go, oh, this is infectious, this isn't. This is rheumatology, it's not infection. They narrow it down, but then the computer's really good at going, well, what is it exactly? Because they have this great memory and go, yeah, you remember 5 things that cause joint pain, fever, and rash. I remember 10 more that you forgot about or you never knew about because there's only been 2 cases in the literature or something. And so they were really good at helping you in that narrow problem space. Okay, so so humans did better out here, the computer did better. And then also computers are really good at combining probabilities. Humans are notoriously bad at combining probabilities just in their head. All right, well, now things are a little bit reversed. So now it turns out that these large language models tools are really good at narrowing, at figuring out where they are in the problem space and narrowing it down and directing it, because they've got lots of patterns, and they've got pattern matching capabilities that the humans had the advantage over them before. So the computer can do better, but then the human can do better when we get down and actually apply it, because these generative AI things, first of all, they generate too much stuff. They chat explain everything, right? You get all this stuff, and then they may get off track. They may confabulate or hallucinate, and so the physician or the nurse or whoever, the humans, can look at that and go, oh, this is nonsense. But this is the important thing, or, oh, I didn't know about this, let me go read about this, I never knew about this, let me see if this is real. And so the humans then are better at figuring out how to apply that, so it's kind of changed the paradigm. Now, they can go off the rails, and when they do, and when they start reasoning along an incorrect line, they often don't correct themselves unless you correct them. You say to them, are you sure that's right? And then they'll say, oh yeah, you're right, it really is this thing, and then they'll get back on track. But if they're left to their own devices, they will just keep going further and further off track. And it's why do they do that? It's because if we call them homonyms, where they're using these tokens, that there might be, for any given set, there might be more than one that they use, and one might be correct, the others might be slightly wrong, and then they pick the next one and the next one and get further off. All right. So where do we go with all this? So we've got our, you know, our informaticians, we've got our generative AI, we've still got our commercial EHRs. What do we do? Well, now we can try to apply generative AI, as my colleagues and I are doing, and to help us with our innovation. And then we have to do an end run around the vendors and the IT departments and figure out how are we gonna get this into content. So what we're doing with our browsing system is we get the data out, that's easy. You know, we have little tables, so we can get the data out, we can build our knowledge base, we can build a viewer, and then we can show that to the clinician. You don't have to interact with the EHR directly. We can show it to the physician next to the EHR, so they can go, well, I can browse the EHR the old fashioned way, you know, go find the labs, then go find a note from that day, and then see what else the note says. Oh, there's a radiology report, then I gotta go look at the radiology report, and then I gotta go back and see which note was I looking at and try and navigate all that stuff. Or they can use our system, which would be this graphical thing, and hopefully we'll connect them all together. We'll see what happens. It's science. We're gonna try and, you know, we're gonna do a study. We'll build some of these knowledge bases with people who are actually seeing real people in their clinic. They'll use this to navigate the record, and then we'll see. We'll do observational studies and find out. Is it better? Okay, so we get the data out. We can create our knowledge. We can use innovation to do that. We can build decision support, we can do innovation for that. We can give that to the users, and then we can have the users make their decisions using our decision support, and then put that back into the workflow somehow. Now, in our case, it's the physician has to go and figure, oh, I'm gonna make this decision, and they go and write their note, or they write their order, or whatever or they tell the patient to do something, whatever it is they're gonna do, it's left to there's a human being in that part. So we can do all that stuff, we've been doing that for decades. All right, now the question will be, what do we do here? So that's still the problem. We've got this EHR, it's a closed system, the vendors don't want us messing around with their code. We got to figure out how do we get things back into the record, and there are ways to do that. Okay, so we can take Epic, for example. And I wasn't sure how to do this, so I asked ChatGPT, and it gave me a link to an Epic site that told me exactly how to do all this stuff. So thank you, ChatGPT. And so I found some of these things, and this is documentation on FHIR, Fast Health Internet Resources, or interchange resources. And it's an HL7 standard, and Epic uses it to both get data out, but also to put some limited data in, if you do it right. So there are these create functions, and they use STU is what is it, standard for trial use, something like that. What is it?
It's basically version 3 and R4 is version 4.
Yeah, but STU is like standard for trial use, so it's not like the official standard or something. But anyway, yeah, so version 3, version 4 of HL7 to actually write things into the EHR to document or put in orders. So that's going to allow us to close the loop. So we have this thing, and what do we do now? What we do is we put a do it button. Right, so remember the Alexa said, would you like me to do that? And I apologize for anybody who's listening to this and has a smart speaker sitting next to their computer, but that's the way it goes. So we put a do it button. Would you like me to do it? Yeah, click there. And then we can build all those interface tools using existing standards to be able to do those things. So I don't have to do 10 things. I just click a button and it goes and puts it on. So I don't have to write it down, log off, log into a different system, and then figure out how to do those things, remember them and so on. Okay. So that's, I think, the approach. Now, so I did a lot of informatics research to figure out what these questions are. We did observational studies. We actually showed people data, and we said, had them think aloud as they were looking at patient records. What are your information needs? What are you going to do now? What questions do you have? And then we collected those with hours and hours of videotape. It was videotape back then. And then we coded them and we figured out, okay, here are the kinds of questions the information needs. Here is the context where they arise. And then here's how we're going to answer them. We're going to build informatics tools to answer them. And that was informatics research in the 90s. Okay, so now in 2025, what do we do? Well, this thing, the computer is able to answer these questions, but what about generating the questions? Can it do that? So do we still need observational research? So I asked ChatGPT, I gave it this case, I created a new session, and I gave it this case, and I said, what are the information needs a physician would have? And it generated a nice list about identifying suspected diagnosis, diagnostic workup. It gave me pages and pages of stuff, but these were the headaches that it gave me. And then I said, what about nurses? And I said, oh, well, the nurses would have these things, and it gave me a different list. Some of them are similar, but some of them are different, like how do you administer the medications? How do you protect the patient's airway? Things that nurses are gonna be more concerned about, shift handoff and coordination of care, psychological and patient-centered concerns. Because there's that note in there somewhere in the record that says the patient's concerned about getting home in time to, getting out of the hospital and taking care of her elderly mother or something like that. And then I said, what about medical students? What do they need to know? And so it gave me a bunch of things that medical students would need to know. And so, wow, I don't have to do the observational studies anymore either, really. Are we getting out of business here? Okay, and then it said how it could help in real time, and it said how it could implement. It gave me ideas about how to implement. So it really put the whole thing together for me. So all I have to do is really just say, here's a case. Now design a system that's gonna help make the patient better, and it'll connect all those dots and put it together. Obviously not that simple, but the idea is the pieces are there. We just have to know how to ask the questions. So, are we out of business? Well, I said, who else has information needs? And it gave me a long list, and it told me what kind of information needs they needed. It was a long list, how it goes on and on, right? Take a look at this list and tell me if anybody's missing. I couldn't believe it. There's somebody missing.
Patient,
What?
the patient's
The
missing.
patient. Patient's not on the list. How could it not put the patient? It even put family members and caregivers at the bottom there, but it didn't put the patient on the list. So I said, what about the patient? And it didn't go, oh, sorry, I forgot about the patient. It just went on. I said, well, the patient would, it just went on. But I had to ask the question. All right, so there's still a role for us humans in this process. All right, how are we doing on time? Hopefully close to the end. Good. So the take-home messages. There are still roles for clinical informatics researchers, I think, in figuring out how are we going to build this workflow, how are we going to test it, and make it better. We can leverage the generative AI and large language models. We have to understand its limitations. Like any other technology, it has limitations. We've got to understand those. We've got to learn how to work with them. It's not a cheat to use them. It's a tool, just like I don't know if none of you know what Index Medicus is probably. Some of maybe Bob knows. Index Medicus was a book published by the National Library of Medicine, and it had all the citations. And they had two books. They had one that was by title, sorted. I forget how it was sorted. It was sorted by author. So you could go to the book and look up all the papers by a particular author. And then there was another book, and that was sorted by mesh term. So you could say, find me all the articles that are about myocardial infarction. So you could go, and it would be pages, 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 of course. And then you'd look through there and you would cross-reference them with a second mesh term. So you could say, well, is paralytic shellfish poisoning in there anywhere? And it was alphabetical, so you could eventually get down to that. Or you could start with paralytic shellfish poisoning and say, and then look and see what other mesh terms the articles were about, and find one on myocardial infarction. And then you, oh, look, there's an article about this. And then you could go write it down, and you go to the stacks, or if you weren't allowed in the stacks, I went to Brown, you were allowed to go in there and do whatever you wanted. But in other places, the National Library of Medicine, you wrote it down, somebody went off and got it. The National Library of Medicine built the L Hill, and L stood for Lister Hill, who was our Lister Hill, our senator. But they built a knowledge base called L Hill, and Medline was built on that. So you could actually do a literature search eventually doing this, but otherwise you had to use the books. And if you wanted the current year, so if you want 2025, they would publish January, and you go and get the January books in February. If it was December and they hadn't published the 2025 compendium, you had to go through 12 books, to 24 books, to get everything on. Plus all the books from the previous year. It was really tedious to do a literature search. You say, now we have PubMed. Is it cheating to use PubMed? No, of course not. We have to know how to ask the question. We don't go, find me all the articles about blah. You got to construct a good query, or you'll get nothing back, or you'll get the wrong things back, or you'll get too much back. And so you got to say, no, I want this mesh term. This is the mesh term. These two mesh terms, and then maybe there's subheadings I'm interested in, or whatever. All right. And then we've got to figure out how to leverage electronic health records to improve workflow. So the electronic health records, they have their own workflow. We're going to be thinking of new ones that are not going to be compatible necessarily with the existing ones. And they'll say, we'll just create a new alert. No, that's not the way. We want to find other ways to do that. But the standards that are coming now are giving us opportunity, of course, to get data out, but also to put knowledge back in. So what we really have to figure out is, how do we put this knowledge in a way that's gonna work for the clinicians, for the patients, for the nurses, for the doctors, for the medical students, for the pharmacists, for the, physical therapists. So they all have a different way of looking at the same information. How do we put that in there, in a way that helps them and doesn't overwhelm? And all of these things, ontology, maybe you saw ontology in there a few times. It comes back over and over again. It's a key thing. Okay, so those are my take-home messages. I want to acknowledge Tiago's fantastic work on all of this. John Osborne's been enormous help with the natural language processing. Matt and his team helping us to get the data out. Nick Timkovich building our tools, and Arushi Jasaniaki, who was a postdoc fellow who did a lot of the work on figuring out the ontology back when we get started. Okay, so I will end with Chark-Friedman's fundamental theorem, which I always interpreted to mean two errors human, but a computer's required to really screw things up. But my corollary to this is that human plus computer is better than computer. I think that's still true. All right, and that is my presentation. So I'll stop sharing. Let's see, there's something in the chat. You have reached the recording limit for your plan. Okay, that's Jeff's note taker. Okay, so nobody's entered any questions, comments. Jeff.
One of the historical criticisms of EHRs has always been it's really a billing system, not really a clinical capture tool. And one of the questions I always ask is it possible or worthwhile to decouple the clinical part from the billing part? Because to your point, a lot of what you're representing in an electronic health record, and your example here is clinical content. That's mostly what's missing, the smarts around it. It'll tell you which code doesn't work for which diagnosis, but it won't tell you which meds, right? Is that even possible? Or, I mean, given all the vendor environment?
Well, so Jeff Gordon's question is, EHRs are criticized or described, let's say, accurately as, if not primarily, at least an important function is billing. Certainly that's how they started. The public health records started as billing systems. And then they added, they said, oh, well, we have lab results, we can show you lab results. And then they said, oh, we have a pharmacy, we can show you medication. Oh, we'll put a little note writer so you can write notes. And the next thing you know, they were calling it an electronic health record because they had notes displaying results, but it was primarily for billing. And so Jeff's question is, can we decouple that or maybe change the emphasis so it's now on the clinical care, the clinical documentation, clinical processes, and less on, no, I think absolutely. Original like paper records were not created for billing. I mean, they were used for billing, but they were created to bring the data to the clinicians. And we wrote notes that way. We didn't have to do the billing. The paper record went to the billing office, and they had people who were experts at figuring out how to do the billing, and they were doing that for decades. And then when we had prospective payment, all that other stuff, billing became more important, had to be more accurate. They even built smart tools to help them do that. There's been a gradual shift now to getting the clinicians to put the data in that there's needed for billing. So we end up like, oh no, you can't just say whatever problem pops in your little head. You got to pick an ICD-10 code. Put those in the record. And so why is that? Do we care about ICD-10? We're reporting to the World Health Organization? Well, apparently we aren't anymore, but we still have to use ICD-10. Why? Because it's used for billing. Okay, so it's changed that way. But Jeff's question is, can we decouple that? I think the answer is definitely yes. People have been trying to do this with natural language processing before 2024. And now with generative AI, large language models, we can figure out how to produce those codes just from the text and the other things, not just the text, but all the other, lab results, which tests were done. The system could theoretically, you should be able to figure out, was this a severe case of this or a mild case of this, and use the appropriate billing codes for that. So I think, we will be able to do it. I'm sure people are working on this. I mean, I see things in the clinical informatics literature about this. Certainly the companies that, sell their products based on this, and, you've got to have accurate. You don't want to miss anything because you want to bill for everything you're entitled to, but you don't want to overcode because then you get slammed with, accused of fraud, and you not only don't get the money you billed for, you don't get any money, and you might get fined and you might get put out of business. So accurate billing is very important. Yeah,
Dr. Cimino, thank you for the talk. It's really nice. Actually, it aligns with what I'm trying to do. Your slide, maybe informatics can help. In that slide, where do you see the AI agents?
slide where maybe informatics can help.
So,
It
yeah,
can help with everything. So it can help figure out what is, taking a context. We used to do a lot of work to figure out if somebody's looking at this lab result, which questions might pop in their head? And we can anticipate and give them an answer to. Now, you can say, here's the context, just put it in there and it'll be ready to go. And you'll say, and then I'll say, oh, help me understand this screen I'm looking at. I said, well, it's showing this lab test and this disease. Is this what you want to know? And if it knows about the patient as well as what's on the screen and it has medical knowledge, you can put all that stuff together. So it can help anticipate information needs, help address those needs, and help us, just not just address the information needs, but actually address the procedures that need to be done, the order writing.
Just one thing, like, which one would you prefer? Human in loop with AI agents or autonomous AI agents?
So the question was, do I prefer humans in the loop or autonomous AI? No, I think humans have to be in the loop. We've taken humans out of the loop in some things like electrocardiogram interpretation, although they're still read by a cardiologist eventually. Nobody looks at the EKG signal anymore. I mean, the cardiologists do. But, the frontline clinicians just look at the little report that comes out of the machine. It turns out that those reports aren't always accurate. But we've come to depend on them because the computer's gotten better than the humans at doing that. I think we have to be careful about over-dependency on these things. Clearly, they hallucinate, confabulate, whatever, and people have to be paying attention to that. So no, I don't think we're ready to turn over medical decision making. Now, in low resource settings where there's no clinician, then maybe that's different, right? So somebody's out in the field and they're not a clinician, they're a barefoot, they call barefoot doctor. Somebody's out in the field and they're, in say Africa, in the middle of Africa, and they're some little village, and they're looking at a person comes in and goes, I have this thing. They go, I don't know. They take a picture of them, they put in a few keywords. The generative AI says, give them this pill. And they go, okay, that may be the best we can do because we don't have the resources to give them a full physical exam and the attention of a board certified, clinician and so on. Then that may be the next best thing. Yeah, first.
I was gonna ask, as patients have complicated histories and end up with very long charts, do you run up against context windows when you're starting to use generative AI for summarizing this?
So the question is, do we run into context windows with very long charts? We haven't explored that. I don't know if John Osborne's on here somewhere, or maybe Ryan Melvin, somebody wants to jump in, they're both on here. If somebody wants to jump in and answer that question of whether with complex notes we run into problems with context. My guess is, just from 50 years, or 60 years of working with computers, is that if they have a problem now, they won't next year, right? That it will get better and better as we improve our computational abilities. But I'm sure that can happen, but it will become the text window, we're talking about a few megabyte, it's not going to be horrible. Anybody want to jump in? Let's see, we haven't explored this enough for this use case. The context size has increased quite a bit, even in the last year.
Yeah, essentially, yeah.
Yeah, that was just a guess based on, the history of computing.
Yeah, for some of the larger models that are out now, the context window is quite large. And so if we were to use those, I think most clinical notes, but not all clinical notes, would fit in that window.
So it's an order of magnitude to get the rest in there. And then, of course, many orders of magnitude to put all the images in. But, we can do things like separate, we can analyze the images separately, pull out features, and then put those features in to a context. So there may be ways to do that with the record too. Like, all right, we can't put the whole record in, but we can process each note one at a time, pull out features, and then that collection of features is much smaller, and that could be the context we use. Especially today's notes, the current notes are just full of junk that people put in that are of no clinical relevance. And we can pull out those things. So what changed from yesterday to today? We have two notes, they look almost identical because they probably were cut and pasted. Somebody modified them a little, pull out the things that are different, and then pull out those features, like compression of images or compression of video. Ryan says, we've been trying this with CT reports and surgeon impression and plans. No problem fitting as many as 7 notes at a time so far. All right. Other questions? Okay, I see I'm overdue for my meeting with my team to build the next generation of electronic health record. So thanks for your attention. And I'll be back in 6 years to tell you where we are, the next version. So, thank you.
As many as 7 notes.
Yeah,
Looking at
that was a
horizon.
smaller number now.
Yeah.
You know, 50 years.
There are 40 pages of notes, but 10 on a page.
Yeah.